quantum algorithm for studies of the properties of spin system and spin-1 tunneling. So please, Khrystyna.
Many thanks for the presentation, and many thanks for the invitation. Give this seminar to present this talk. So this is very important for me to discuss with you our recent results on quantum programming, quantum information. So first of all, I would like to share my screen, to share my presentation.
Please share.
Can you see my presentation?
Yes, we can. Everything is fine.
So let's start discuss the scientific results. Scientific results on quantum algorithms for studies of properties of spin systems and spin-1 tunneling. So first of all, I would like to start with the main problem of quantum mechanics, finding or detection of the energy levels of physical systems. And this problem can be solved with quantum programming. And we proposed the algorithm for finding the energy levels of spin systems and various physical systems with the help of studies of evolution of a mean value of operator, which anti-commutes with Hamiltonian or ancillar spin or ancillar qubit. So let's discuss the details. So if you have a spin system, or if you have a physical system which is described with Hamiltonian, and we know the operator which anti-commutes with this Hamiltonian. So there is some kind of symmetry in the case of this existence. So we have this, the spectrum of the system is symmetric with respect to this transformation. In this case, we can find the energy levels of a system described as Hamiltonian with the help of studies of the mean value of operator A. So why do we can do this? This is because if you consider the mean value of this operator which anti-commutes, and if you consider a simple representation, so we often do this in quantum mechanics, so we can rewrite this mean value, the mean value of this operator with omega. Omega, they are frequencies, so they are related with the energies. So the mean value can be, in the case of the when operator anti-commutes with Hamiltonian, we can do all these transformations and obtain this expression. So on the basis of this result, we see that if we consider Fourier transform, we obtain that the value A, which depends on the omega, has very clear, very sharp peaks, which correspond to the points, to the properties of our system, to the energy levels. So we can see from here that we have this delta peaks, which corresponds to points 2 multiplied by omega I. So we use this theoretical result in our quantum programming, and on the basis of this result, we studied, I have to say that these are simple models of spin systems to discuss the results of quantum programming to check if this algorithm can be used on our real quantum devices. So we considered Eisen model on square lattice. So the Hamiltonian is written here. Why do we consider such interactions? This is because of the structure of the IBM's quantum computer. So we considered this part of this device. And in this case, the operator which anti-commutes with the Hamiltonian is this product of the sigma x operators. And then on the basis of studies of the mean value of this operator, we obtained the spectrum of the system. Here on this slide, you can see the protocol, quantum protocol for studies of these mean values. So we prepared this quantum state, and then we use rotation in order to calculate the mean value of the sigma x operators. And then on the basis of the measurement, we obtain this mean value. So we detect this mean value in different moments of time, and so we study the evolution of this mean value. What we obtained is presented here. So we obtained this crosses correspond to the results of quantum measurement, and the line is the result of theoretical studies. So first of all, when we saw this picture, we thought that it's some kind of bad result, because we have very bad agreement of the results of quantum calculations with results of theoretical studies. But even in this case, in the case of this quantum errors, we obtained peaks which correspond to the energy levels of the system. Here you can see the results of calculations on quantum simulators. So they are some kind of theoretical results, and these are results from IBM's quantum device. So this is just only one example. In our studies, in our papers, we presented different models, and we obtained results for the energy levels of the spin systems. This result is, I have to say, the worst result because of this quantum errors and because of this some kind of complicated system and some kind of complicated gate expensive protocol. But even in this case, we obtained good agreement, so we obtained these results. On the basis of this, we can say that our algorithm is noise resistant. Also, what we have done is that we generalize this method to the case when we cannot find the operator which anti-commutes with Hamiltonian does not exist. So in this case, we propose to construct the total Hamiltonian. So we construct this Hamiltonian in very simple way. So we just multiply our Hamiltonian on sigma z corresponding to some additional spin or probe spin or ancilla cubic. In this case, we can see that we, in all these cases, for arbitrary H or arbitrary Hamiltonians, we can find the operators which anti-commute, and they are very simple. They are sigma x and sigma y. So we studied different systems on the basis of this method, on the basis of this algorithm, and the general protocol for the studies is the following. So we have to prepare the initial state. We consider the state to be plus plus plus. So this is superposition of all basis quantum states of n qubits, n plus 1 in this case. Also, we have to prepare this operator of evolution corresponding to this system and with this total Hamiltonian. And then we have to consider the evolution of the mean value of some operator, which can be sigma x or sigma y. Then we studied also different models, and we considered the case which is quite simple, but not so trivial, because we have here the operators which do not commute, and in this case we construct this total Hamiltonian, and we found the way to prepare the operator of evolution in this case of non-commuting operators. This is protocol for this study, so we used controlled unitary operator and also phase gate. This is because of gate identities we found during our research studies. And this protocol was considered to study the energy levels of this spin system. And you can see from this plot that we obtained quite good, very good agreement of the results of quantum calculation on the IBM's quantum device. They are represented by crosses, and the results of theoretical studies, which are represented by line. And the peaks, these peaks correspond to the energy levels. So the methods are quite good for even for studies of the energy levels of spin system in our recent devices, on our quantum devices, which already exist. And if you are interested in details or other results, because I present just few examples, please consider these papers. And these papers were published and we obtained together, the results were obtained together with Professor Tkachuk, Hanna Lab. So what about another problem? We also studied the spin-1 tunneling on a quantum device. So we proposed quantum protocol for studies of this effect. First of all, I have to discuss the spin-1 realization on a quantum device with qubits. So we can represent the spin-1 operator with operators of spin-1/2 with the following. So this is well known. This is a result from this paper, for instance. And with the help of this representation, we can study spin-1 systems. So to consider, sorry for this mistake. So here, of course, we have only one H. So here you can see the Hamiltonian, which corresponds to the spin-1 tunneling. So this Hamiltonian is given by this expression, and this is the expression which is rewritten with the help of operators of spin-1/2. So considering this representation, then we can create and represent this operator of evolution corresponding to this Hamiltonian, so we can study this spin-1 system on a quantum device. And then we considered the mean value of this operator, and this is a quantum protocol for this study. So we prepare this state, and then we consider this measurement to obtain this mean values and obtain this result. So we can see the oscillations which correspond to the tunneling. Also, we detect the energy levels splitting as in result of tunneling with the help of our method of studies of the energy levels. And the results are presented in this paper. If you are interested in more details, please consider this paper. Also, the result was obtained with Professor Tkachuk. Then, what about other interesting results of spin systems with quantum programming? I have to say that the entailment is the fascinating property and very basis property in quantum programming, very important property in quantum programming. So we studied the entailment of quantum states of spin systems, and due to the result of this paper, we have the relation of the entailment with the mean spin. And this mean spin can be detected with quantum programming, so we can detect the entailment with the help of this relation for various quantum states. We considered quantum graph states. Why do we need these states? First of all, the motivation is these states are entailment states, and these states can be represented by graphs. So we can map quantum world to classical one. So we have some kind of representation. So with the help of methods of quantum programming, we can study the graphs, classical systems, and with the help of methods of graphs theory, we can consider some properties in quantum world. So if you consider a very simple graph, for instance, you have to say what do you mean that this graph is related to quantum state or quantum state is related to a graph. So the most simple way of representation of graph with quantum state is to map each node to a qubit. So you have, if you can have graph with 4 nodes, you have 4-qubit system, sorry. Then the link between these nodes can be represented with 2-qubit gates or interaction in this system. So let's consider the graph states which correspond to Eisen model. So the most simple case is the Eisen model. And in this case, we construct this quantum graph state with the help of this operator, the operator of evolution, which corresponds to the Eisen model. And this is 2-qubit operator, which is represented also here. And on the basis of studies of the entanglement of this quantum graph states, we found that the entanglement is related with the degree of vertex. So, or the degree of node. So the degree of node is related with entanglement is because, of course, because of these interactions, but we have very clear this relation. This relation is very simple and very clear. So this n with index L is the degree of vertex corresponding to spin or qubit with index L. Then we studied this relation on quantum computers. So we considered very different quantum graph states, and very interesting example, of course, is complete graph. We construct this quantum graph state and measure the entanglement. So to do this, we consider the mean values of sigma x, sigma y, sigma z operators, and we can calculate all these values because of this identity. So we can use measurement in standard biases to obtain these mean values, and we obtain this results of the crosses correspond to the results of quantum measurements, and the line represents the results of theoretical studies. Also, we considered multi-qubit quantum graph states, which are constructed with the help of controlled phase gates. So these quantum graph states are also related to Eisen model, but it's more complicated interactions. And we also studied the entanglement in this case, and we obtained this. In this case, we have also the relation of the entanglement with the vertex degree. And the entanglement, of course, depends on the parameters of the state. We have all these things, all these dependencies. I studied this entanglement with quantum programming. This was done with my PhD student, Natalia Susulovska. You can consider this paper in order to find more details. Then, what about other properties of spin systems and other properties of graphs? So we considered the geometric properties of graph states of spin system with, of course, with Eisen interaction. This is the most simple case of spin systems, and this spin systems can be in a simple way modeled with the help of quantum programming. So we considered this Hamiltonian and also this state. The initial state is 0 state, as it is in quantum device. Then, if you consider the mean values of Hamiltonian, we obtained that these mean values are related with the number of edges in graph, links in graph. So this K2 is the number of the total number of edges in graph. Also, this value is related with the number of triangles in graph. So this K3 is the number of triangles in graph. And this value, this mean value of the Hamiltonian, is related with the total number of edges or links in graph, and also with the K2, and also with K4, which is the total number of squares in graph. So we have a relation of quantum properties. They are mean values of Hamiltonian in different powers. With classical properties, they are number of triangles, number of squares, and total number of links in graph. So we can calculate with the help of quantum programming these classical values for different graphs. And with development of quantum devices, quantum processors, we expect that we obtain we achieve this quantum supremacy in solving this problem, because to obtain the number of triangles, we have just calculate this value. To obtain the number of squares, we have to calculate this value and also this value. So we can do this on quantum devices, and we have done this on a quantum device, on IBM's quantum devices. So there are different methods to calculate the mean values of Hamiltonian, and maybe the most general case is to consider the operator of evolution and the mean value of the operator of evolution, and to consider this expansion. And here we obtain this mean value of h over 2, and this value is needed to find the total number of edges in the graph. Of course, in each particular case, we can find expression for this and obtain these correlators which have to be calculated. We also have done this and obtained these results on a quantum device. So what about the results? For instance, for quantum graph state corresponding to triangle or spin system with this Hamiltonian. So we have that the interaction in our spin system can be described with triangle. So we have these three terms, and we have this operator of evolution, and this state is quantum graph state corresponding to triangle. This state can be presented with, can be prepared with quantum protocol, which is presented here. Then, on the basis of the results of measurement, we can obtain our mean values. We need to calculate this total number of links and total number of triangles, number of squares. Of course, in this case, number of squares is equal to 0. Number of links is 3, and number of triangles is 1. It's very simple. It's very simple toy model. It's just to check if our algorithm works, and we obtained a good agreement of the results of quantum calculation. So you can see that the results, as in previous slides, the results are represented with crosses, and the line represents the result of analytical studies. And we obtained all these things we need to find the number of triangles and squares. So I have to say that more details you can find here in our paper, also published with Professor Tkachuk and Hanna Laba. We also consider the different quantum graph states. We consider squares, chains, and other spin systems. And before I thank for your attention, I'd like to generalize that we have different algorithms, novel quantum algorithms for studies different properties of spin system. First of all, we can detect with quantum programming the energy levels, we can detect with quantum programming the entanglement, we can consider spin-1 tunneling, and also we can study classical properties of graph in graph theory, for instance, number of triangles, number of squares. And many thanks for your attention and many thanks for your invitation. So it's very pleasant to be here. Thank you.
So time for questions. So please, Andrei.
Hi, Khrystyna. It's nice to see you in Kiev, at least electronically, yeah, virtually. Yeah, hopefully in the nearest future we will see you here in a physical state. And my question is, yeah, yeah.
It can be very soon, of course.
Yeah, and my question is about your nice algorithm about to find eigenvalues of Hamiltonians. And maybe it's a little bit naive, but it's clear that your algorithm should work when you have some correlation between qubits. Yeah, so something like this. And can you identify a resource for your algorithm? Is it quantum entanglement or some other kind of quantum correlations? Is it possible to give answer on such question now, or?
Very important question. So, of course, in our algorithm, we need quantum entanglement because, for instance, in the case of ancilla qubit, in the case of total Hamiltonian, which is constructed here. So if we consider the operator of evolution with this total Hamiltonian, so because of this interaction, we create entanglement. So the resource is entanglement. The resource of usage of this ancilla qubit is entanglement. You can see from here, so we need this controlled operator, so we need to create the entanglement state. Also, at the beginning, we consider these operators Adamor gates, which create our superposition. So we also consider here this parallelism of quantum computing. So in parallel way, we calculate different various things and we manipulate with this basis state to detect these new values. So thank you. It's very, very important, very interesting question. We very often discuss what is the most important thing in our algorithms at the department. So thank you.
Okay, thank you.
Okay, question from Bogdan.
Excuse me, thank you for the presentation. Interesting. Bogdan, do you know maybe? Okay, my question is, hello. What additional information about the geometrical state, geometrical characteristic of state can obtain after measuring this state?
So with the help of quantum measurement, we can do the quantum tomography. So we can find all the parameters of quantum states. That the algorithms of quantum tomography are based on this measurement of different correlators. So with the help of quantum measurement, we can find all the parameters, we can detect the states, therefore we can find all these properties. If I understand the question correctly, so this is my answer. If not, please repeat the question.
Thank you.
So, Sergei Shevchenko from online has a question.
Yeah, thank you. Khrystyna, it is very inspiring to see that you use realistic quantum computers for diverse problems and that you successfully solve them. My question is about quantum computers. Which ones do you use? I'm asking because we tried several processors and we found that they are very different. They have different parameters, decoherent rates, etc. And also we even found that there exists IBM Q Kiev. Do you know about this? And does it really exist in Kiev, or it's simply a name?
Thank you for the question. So maybe from the end. So the names of quantum devices are related with different cities, different towns, but they are not located in these places. They are located mostly in the United States. And before the September 2023, we had free access to IBM's quantum device. Unfortunately, because of the war, now we have not this access, but we have very, very intensive, I have to say, communication with IBM to obtain this access. So before this time, we considered different quantum devices for our studies. They are 7 quantum devices. Of course, the properties of the devices depend even on the time when you calculate. So if I made some calculations for instance, in the morning, and then I use the same device in the evening, you can see that the errors, the gate errors, the errors of measurements are different. So it depends. Here you can see that used IBM Bogota, IBM Q Bogota. We considered also IBM Q Melbourne. Nowadays, we also study, we also make calculations on real quantum devices, and I use Rigetti quantum devices. Also, we use IBM's quantum devices, but in a more complicated way. So
okay, so
that's answer.
Thank you.
Thank you, Khrystyna. So we have one more question, maybe last before the break. So Alexei has no. So this your.
This is Michenko Yuri, BITP. I have a simple naive question concerning the average quantity A. Why do you choose such a triple multiple of sigma? What is the physical motivation for taking such an average, of choosing this operator for averaging?
This one? This one?
Yes.
This is because this operator anti-commutes with the Hamiltonian. So we have different terms, and with each term, the operator has to anti-commute. So this operator has to, the anti-commutator of this operator with H has to be equal to 0. Therefore, we found this expression. So you can see that this operator, because of this sigma 0x anti-commute with this one. Also this operator, because of this sigma 2x anti-commute with this one, and so on. You can check all these terms.
But there are no other physical quantities which include this operator and you need in the future.
So you can also create another operator which anti-commute. For instance, you can consider sigma y 0, sigma y 2, sigma 13, or sigma y 13, sorry. So the mean value of this operator in quantum state is the correlator. So we considered.
Okay, thank you.
Yeah.
Oh, I don't see more questions online. I don't see also. So, Khrystyna, thank you very much. Let us send the speaker again.
Thank you very much. Thank you.
And now is the time for a coffee break for 15 minutes.